always thank the audience. Creek, hold. What? How do I... Man, I don't know how many people are watching. Who's watching now? Nobody? Why don't I see who's watching? Well, I cannot see that. Cool. So let's move on, okay? So it's before I was so rudely interrupted by the technical difficulties, I was saying that we can view any problem like a game, okay? Do you agree with this? So let's take this game, for example, the 8 puzzle, okay? We can model the state of the game as a permutation, right? Like you can see that we have 9 entities that we can permute, right? We have 1, 2, 3, 4, 5 up until 8, and this blank we can call it 0, okay? So we have the numbers from 0 to 8. So actually this initial state can be viewed as a permutation of these numbers. Do you agree? So in order to advance in the game, you have some actions, okay? So in every problem, to solve the problem, you need to be dynamic and find some ways to get from the initial state, which is problematic, into a state in which you find a solution to the problem. So therefore, in this particular case, you can move to the left, like Beyonce. You can move up, down, or to the right, okay? So based on all these actions, you will create other intermediary states of the game, right? But you can see that when you try to solve computer problems with the most, I don't know, the most successful technique known to man in computer science, okay? At least theoretically, aka brute force or backtracking, right? So if we think about brute force, okay, I would like to think I didn't do that, man. Somebody's tampering with my PC. So if we think about brute force, okay, I will reiterate the example about stealing a car, okay, or borrowing it, okay. So you wanna make not a car, a bike. We wanna make one bike yours, okay, but it's guarded by a cipher of 4 digital numbers, digital digits, okay. So the only thing you can do is to try all the different combinations because you don't have any other information regarding the problem, right? So the only thing you know is that there are 10 to the power 4 possibilities, and each and every one has the same chance of being the locked combination, okay? So let's say you don't have any sort of other clues like which digits are the most worn off or something, or you know nothing about the owner of the bike or something, okay? So in this particular case, the only solution, the only way to solve the problem is by doing brute force. So even if I'm talking about this particular 8 puzzle game, or if I'm talking about running all the combinations for a locker, or solving some more advanced problems using computers, we still are faced with the same realm of searching for a solution in a search space. Do you agree? So the thing is, I can model the problem of decoding a cipher in the same way. Like the initial state is just a state in which I didn't choose any value for any of the digits in the cipher. Now, if I start with the least significant one, I can assign either of the values 0 to 8 to 9 to that first digit, right? And then I move into a state in which that digit was set to that value. And from that point on, I will generate another collection of states that has this first digit already generated to 0 in this case, and then all the other possibilities for the second digit. and so on and so forth. Okay, so this is 0, 1, 0, 2, 0, blah 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 blah. So the point I'm trying to make here is that you can view any problem, no matter how complex it is, you can model it as a way to go from a starting state, which is very problematic, into a destination state in which you solve the problem, right? So this is regardless of the nature of the problem. If you are able to model a problem such that it becomes a search problem, then it means you can perform search algorithms in order to solve the problem. So you somehow have to change the point of view of the problem. So the statement of the problem can be given in one way. So in this case, it's a cipher of digits, and in this case, it's an 8-slide puzzle, or it's a Sudoku board, or it's a chess game, or it's any other problem. It doesn't matter what it is, because you will change that mind state for the problem into a search space. Okay, you will envision looking for a solution to a problem differently. So this is what you need to do first. You need to get into a different thinking paradigm. Okay, so okay, I have the problem, and the problem usually is comprised of variables with definition domains for each variable. Okay, so in the case of the cipher, the variables are the digits, and the domains are the possible values for each digit. Okay, so the first one has a domain from 0 to 9, the second one has a domain from 0 to 9, and the Cartesian products of all the represent all the combinations. Okay, that's why I get 10,000 valid candidates for valid combinations, and I need to search each and every one of them to see if it's one of the solutions. Okay, so okay, this was brute force. Okay, what brute force does is, let's envision the search space like this. You start from the top of a tree, and then at each level you generate the outcomes that may occur by choosing one variable from that state. Okay, now this is like parallel universes, right? So for each of these choices you generate a different universe based on your decision, but in that particular universe you can still choose values for the next variable. So this generates a subtree for each of the possible outcomes that emerge if you have chosen this particular value for this variable at that point, or that particular variable, or so on and so forth. Okay, so usually what a brute force algorithm does is he goes as deep as he can, or it. Okay, sorry. So it goes as deep as it can into a branch of this tree in which all the variables have been attributed values, and then checks if that particular combination of values per variables represents in fact a solution to the problem. And what it does, it linearly checks all the leaves of this giant tree one by one to see if they're solutions or not. Okay, so that is why the brute force method is also called generate and test, because you use all this manner to simply generate all the Cartesian product of all the combinations of the domains of the variables in your problem, and then you check. Okay, clearly this is only has a 100% success rate from a mathematical perspective. Okay, we can solve any problem using brute force, but ain't nobody got time for that. Okay, it's because it takes too long. Okay, think about it. So if I have like n variables, called xn, okay, and each one of those belong to a domain of definition. Let's call it d of xn. This generation of the Cartesian product for all the domains, for all the variables, would be like the product for I from 0 to n minus 1, let's say, of the cardinals of this domain. So I have to multiply all the cardinals, okay? So this easily becomes a very, very impressive number, okay, that cannot be like, even if we use the best computers we have today, it will still take longer for the real problems of today. For the NP complete problem, it will take longer than the time that has occurred from Big Bang till now, okay? So it's a good mathematical way of tackling any problem, but it doesn't work in practice, okay? And what it lacks, or why this happens, is because it lacks intelligence. It's based on the principle that we put the computer to work and not to think about the problem, okay? So you just generate all the possible outcomes, and without any justification or prior thinking, you just check it if it's okay or not, okay? So this is mechanical, it's unintelligent. The intelligence comes from, I mean, the first idea of intelligence, of artificial intelligence, comes from the next of perfection to the brute force algorithm, okay? I'm gonna put here the notions that we talked so far. So this is brute force algorithm, and now I'm gonna talk about backtracking, okay? So to perfect the brute force algorithm, to use the first amount of intelligence ever in an algorithm, what we do is we don't generate all the solution at once. We don't go all the way down from the top of the tree all the way down to a leaf, but we try to generate the solution gradually. I mean, here, as I said, here we have nothing. Here we choose variable 0 for the first digit in the cipher. Here we chose the 0 for the first and the second digit in the cipher, and so on. How does this change things? Is that at any point here or here, I'm faced with a decision. What I created so far, is it okay from the perspective of the problem or not? So if it is, I keep on going. If it's not, I need not bother with all this subtree generated here. Do you agree with this? So all this leads to failure, and being able to not do actions that most certainly lead to failure is the first sign of intelligence. Avoid unnecessary effort that you know it will not lead to good results. So, of course, it's not artificial intelligence, but the first algorithm that includes some sort of intelligence is backtracking. By doing this, avoiding a whole range of sub-search spaces if you already know they're not good, right? So whereas the brute force algorithm would exhaustively search all these possibilities, the backtracking will search at most that. Why do I say that? Well, let's take the case of the bicycle stealing problem, right? I know it doesn't have a good title. Again, I will recommend the movie called Ladri di Biciclette. It's a very good neo-classic Italian movie. Bicycle thieves, yeah, exactly. So watch it, okay? So if you were to steal a bike you don't know nothing about, even if you do backtracking, at each step you will have 0 clues in order to discern whether to eliminate a bunch of possible candidates or not. So in the worst cases, even if you do backtracking, you in fact do brute force, because you take into consideration all of the possibilities and you cannot exclude any of them because of lack of evidence, right? So this is backtracking, okay? So we reviewed these 2 ways of searching for solution to a problem in a problem search space. So a problem search space can be seen as an initial state that leads to some a tree or a graph. We'll talk immediately after this distinction of intermediary states, some of which somewhere down the path may be solutions to the problem, okay? So what we need to do is to explore this space in order to finally arrive on a solution, okay? So what I like how I like to plastically illustrate this is like you're looking for needles in a haystack, okay? And what brute force and backtracking does is like if you want to locate them using some metal detectors, okay? So you have all these huge haystack and you go and you try to find all the needles. So then you scan line by line, exhaustively without leaving anything to chance. You scan all the perimeter and it guarantees that you got all the solutions, okay? But of course it will take a week for a small amount of terrain, okay? So this is why it's not feasible in practice, okay? By the way, I encourage you to look on Allen Iverson's practice video if you have the time. It's hilarious, okay? So let's move on. So these algorithms perform exhaustive search. I mean, they look everywhere and don't leave anything to chance, okay? And that's what makes them rather unpractical, okay? They're like a very, very, I don't know, anal individual who just like doesn't leave anything to chance, you know? No, he will soon lose a lot of friends and alienate people, right? Graphic tablet. I still read the same bad drawer with it's the hand that writes, not the tablet that does the difference. Restanțierul anilor, oh mg. Welcome to the jungle, my friend. Okay, I will next time. I will bring improvements to the quality of my streams next time. Okay, this was my first time, so I'm so excited. Okay, hope you guys are too. Cool. So let's move on. Okay, the thing is that we need something more practical. Okay, because nobody cares about theory, right? In theory, we can solve any problem with backtracking and brute force, okay? We talked the other time about what? How to search. Can I erase the blackboard? Can I use another one? Okay, let's do this thing. And another one more. Another one. Okay. Okay, so having this in mind, okay, let's check the unexhaustive algorithms for search. Okay, so let's say we start from an abstract initial state, okay? Now we have some actions that can lead us to some other states, okay? And now there's the discussion between how my search space is organized, okay? Because it may be organized as a tree, okay? As it is in the cipher problem, right? Because all the subspaces generated here and here by any branches are different from one another. They don't overlap. But how about the 8 slider problem? Well, it is clear that if I do the opposite. If I I slid to the left, now I slid back to the right, I move back to this state, okay? And maybe after some multiple slidings of the board, I can arrive into an already existent state, okay? Do you agree? So therefore I have two architectures for the search space. I can either search in a tree or in a graph-like structure, okay? But since a tree is a reduction of an abstraction of a graph, then I should focus on how to search for stuff in graphs, okay? So let's draw some example graph here, okay? It's a directed graph, okay? You can, as I said before, if you think about it, you can define anything as a graph in computer science. So a variable is just a graph with only one node. An array or a linked list is just a linking of these nodes one after the other in a linear fashion, right? So then you have either an index or a next pointer to go to the next one, but they're all in a linear fashion. Okay, sometimes you need to model things that are not linear, correct? For example, like your genealogy, where do you come from, right? So at some point you should have to bump into trees, like boom. Just this is the if statement. If you create another analogy to programming, you have to agree that this here is an if statement. If the condition here holds, you go this way. If not, you go that way. Okay? So if this is the if statement, how do I turn from a tree to a graph? You name it. Yeah, you figured it out. It's using cycles, aka loops, aka the repetitive statement while or for, right? These guys, if we introduce these guys into the equation, we're getting to graphs, okay? We can come back to a place we were before, and this kind of makes things a little bit more difficult, right? But not entirely. So let's say we start with graphs, okay? I will erase the doodles on the right side of the board. So let's create a very compelling graph. So you know, guys, the guys in my class, you know that you will still have that homework of performing search algorithms in graphs, okay? We're gonna again, we're gonna talk about it a little bit, so I know that you at least know that, right? Okay, so damn, it's 5 o'clock already. Okay. Let me announce the other guys with whom I have a course afterward that they can join in on this one, okay? Because it's gonna cover the same topic, okay? I'm gonna just one small break, okay? I mean, it's not a break, just bear with me. Bear with, okay? Dudes, really, like, if you're in the UK, I guess you can watch that thing on the TV or something, on the telly. Like, watch Miranda. It's a hilarious TV show. So, okay. Okay, sorry for the break, okay? We're back from outer space. I just came here to... Bă, dar nu știu versul, I don't know the lyrics to... I should have changed that stupid lock, I should have make you leave the key. Okay. But now go, walk out the door. Okay, let's see what these algorithms are, right? So, the thing is, they still do, to some extent, exhaustive search, but they do it in a more orderly fashion, based on some intuitions, let's say, okay? So intuition is a very, very important term with respect to artificial intelligence, okay? Because intuition is not something that can be easily I don't know, cloned into a machine. But it's something we people have and machines don't. Okay, so if you want to create real artificial intelligence, you need to mimic human intuition. Like, I don't know all the facts, man, but I know that I have a gut feeling that that's the right case. Without all the computations, without wasting time, I just feel it, man. You know? That hunch is not characteristic to machines. Machines need to take it, they're like Doctor Strange, you know, they need to take into consideration all the possible futures, and then based on which one gets the best result, they act. Okay, so how do we model hunches, huh? You guys still with me? Write something on the chat. Creak, creak, creak. Grumpy biscuit. Yeah. Oh. Okay, guys. So, how do I search in a graph? Okay. So, if I was to search in a tree, the things were pretty easy, because in a tree you cannot go back to a state you've already been to. Okay. But here, as we have cycles, we need to track the fact that we don't visit a node that was visited before. So I need to have some sort of a data structure to memorize that, okay? So let's call it visited, okay? So this is the visited structure, okay? Let's give them proper names, 0, 1, 2. I will not get into many details because most of you know these things, but this is just for creating a perspective for what's to come, okay? I hope you can bear with me again. Yeah, dude, who's Clooney? George Clooney? So, for each of these particular nodes, I need to keep track, so based on their IDs, blah, 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 blah. Let me do a quick life hack here. Do I have them all? Yeah, sure. Okay. So okay. So of course each search comes with a starting point. Okay, you need to have some inception point, let's say, okay, insertion point from which you can start your search. Okay, so this is called the starting point. Okay, again, I will review these guys so you don't have the luxury to tell me, but we didn't cover it. You wrote code like you said, and it's not clear to all of us and shit like that. Okay, so the starting for me, the starting statement is 0. Okay, so of course I'm gonna set it as being visited, right? So let's put a little v here. Okay, in order to model this, I'm gonna say that I have some sort of collection of entities, and I'm gonna push s into the visited set. On the other hand, I need to to use an auxiliary structure to model my way of passing through all these nodes. Okay, I'm gonna call it C. It's just a collection, it's an abstract collection, it doesn't matter what it is, but I'm gonna push this starting state in it. Okay, and now hear me out, man. I mean, all these algorithms are very straightforward and simple. I mean, all of the algorithms, if you have the background, the necessary background to understand what they do, they become easy to understand. Okay, so just hear me out, like logically, right? You start from this node and you say while my container C, whichever it is not empty. Okay, so it's not. As long as it's not empty, I'm gonna keep on doing my thing. Okay, so okay, all right, let's move it to the left a little bit, to the right, sorry. So let's say first I pop one out of this, right? It's too small, right, guys? I should increase the... How do I increase the size of the... Okay, let me do it like that. Cool. So 24, I guess, 28, let's say. Okay, cool. So I'm gonna say current is C pop. Okay, I just take the pop is an abstract method. It doesn't matter what it does, it just takes one element from the very abstract container called C. Okay, you don't know what it is, it just, you know, it has that function. Okay, so this current node, so if you look at what I did, I just put this guy, so this C will represent the boundary of exploration for me. Okay, now it only contains this guy. Okay, but now I pop it out, so the container will hold nothing for the moment. Okay, but then what I do with this current dude counts. Okay, so I can access, based on the graph, I can access the neighbors of this current node. For each neighbor in, let's call it the graph get neighbors for the current node. So usually a graph implementation gives me a way to access the nodes adjacent to the current node. Okay, in my case these are 1, 2 and 3. Okay, so for each neighbor in this, let's do a kind of a Python version of this. First I need to check if neighbor was not visited, so it's not in V. Okay, once I do that, and the neighbor is not in V. It's not been visited so far. It's straightforward, right, guys? It should be straightforward. It should say that v.push neighbor, because now I have visited it, and then I also put it inside my exploration vicinity, right? So I'm gonna push it into C as well. Okay. So it kind of, I mean, if you ask me, it's kind of logical, right? So at each point I take an element from the container, I look at the unvisited neighbors, and then I relax the boundary of C. You know, now once I do this, I relax the boundaries of this, including all this is the visited space, okay? So at each time you pop something, the first thing you need to do is check if solution. Okay? If solution of current, you just get out and return the path to that solution. Okay, we'll talk about that later. Okay, so see, so it's not DFS or BFS or Dijkstra or anything. It's just an abstract umbrella on top of everything. It's your basic search algorithms, right? Being a programmer doesn't mean just writing code, man. It means finding patterns, right? So this is a pattern of search algorithms. All the search algorithms, be it like BFS, DFS, Dijkstra, A-star, they all follow the same abstract structure of code, right? You have a container, you put an initial state in the container, then while that container is not empty, you take, in whichever fashion you like, you take one element from the container, check its unvisited neighbors, and push those into the container. And after you, at each turn, after you take an element from the container, it doesn't matter if that container is a stack or a queue or a priority queue, it doesn't matter, it can be either, okay? You have the actions of push and pop, of adding element and extracting elements into that container, regardless if it's a stack or a queue or a priority queue, okay? So this is the generic version of any search algorithm, okay? This is still exhaustive search for solutions, right? But now we will see what changes, okay? So let's go on, okay? So do you guys follow this? This is it. Questions so far? Please write them if you can. If some of the guys who are like here in the chat room and still have questions, you can write them, okay? If not, we're moving on. Yeah. So the if is in between this line and this line. The if comes here, right? Come on, man. Let's stick to the chase, okay? We'll talk about basketball later on. So what I want to know is that you got this, right? The father, are you with me? AFK, I guess. Okay, so we're moving on. Okay, so now, as I said, this C is abstract. Okay, it can be any container. Okay, but if this container is a stack, then we exhibit some behavior. If in turn this container is a queue, we can notice some other way of searching in this graph. But however, if we have a priority queue, which is like a queue only better. Okay, so what's a priority queue? Okay, in a priority queue, you don't only have objects. You have some pairs of priority and object. Okay, so actually it's the same. What is the philosophy? You always add at the back of the queue. This is an add, and you always remove from the front of the queue. Okay, so it's first in, first out service. Okay, like in the supermarket. Okay, in a stack of dirty dishes, you always take the last one first. So this is where you add stuff. So you add from the same point, you remove from the same point you add it. Okay, so it's last in, first out. This is LIFO and FIFO. Okay, we're not going to details because I bored you already with it. Okay, but the most interesting part is the priority queue. Okay, here you introduce an element here, but not only the element, it's priority to, right? So you have the P and the object you introduce, and now what happens is that it doesn't remain there. Okay, usually we talked about this. I won't get into details. Okay, so usually this priority queue is implemented on a heap, meaning that a heap is a binary, complete, and balanced tree. Okay, which means every node, is including the root node, has 1, 2, or 0, 1, or 2 kids. Okay, the nodes with 0 kids are called leaves. You cannot have the gaps in your tree like this. So a heap should be complete. I mean, I cannot go and fill in the rightmost child before I fill the leftmost child. Okay, so I go like this when I put kids inside this tree. Okay, so first I complete the leftmost child, then the rightmost child, then the leftmost child to the leftmost child, then the rightmost child to the leftmost child, then the leftmost child to the rightmost child, then the rightmost child to the rightmost child. So I complete all the layers, I don't create gaps, and then I go to the next layer. Okay, which translates into a structure. You can see that a tree like this doesn't need a tree structure to be modeled. It can also be modeled on an array. If we call this the father of them all, and this is the leftmost child, this is the rightmost child, and then let's say that this is the leftmost child to the leftmost child, and the rightmost child to the leftmost child, and then this is the leftmost child to the rightmost child, and so on. You can clearly see that only based on their indices I can locate the leftmost and the rightmost children very easily. Okay, but always if you look at this typical representation of a queue, you enter here, you come back, you get out from here. It's the same thing with a small twist. Okay, I also put an element here to the far down and to the left, right? So this is where I also always insert elements so that I don't have gaps in this tree. So usually, and not coincidentally, this is the last element of the array, right? The one was not being, if the array is completed so far, the next element I have to introduce is clearly this one, right? And also, all these guys have fathers, right? So I can move from, if I insert an element here, if I take the index from here, let's say C, and I deduct 1 and I split it to 2, it will give me a number which is in fact the number of its parent, okay? So the priority queue is just like a queue, but I also insert at the last element, and then I compare the value for the priority of the last element with the value of the priority for its father, and if they're not in the right order, I just swap them, and this guy becomes the father, right? The Oedipus complex, right? So then I don't stop it until I reach the top, or the guys are in the right order, okay? So this is adding, okay? The number of steps performed this way, I will not get into details again, is logarithmic, right? Here it takes O of 1 to, so the complexity of adding and removing is O of 1 here, and also here. However, as it's clear, right? I mean, I don't have to do more than one step at each time. If I add something here, it will take one move. If I extract something from here, it will take one move, right? So also here, if I use an array, a dynamic array, it's the same thing. However, here I need logarithmic time or complexity for each operation, because at each removal or addition, I either have to go on this graph from bottom up or from top down, and the height of a complete balanced tree is, with n nodes, is indeed logarithm of n, okay? So you can see that there's not much difference between a regular queue and a priority queue. What changes is that when I introduce something at the back of the queue, I have to compare it with its father and its father, and so on and so forth in a logarithmic manner, up until it reaches the position respected by a min or max heap, which is that any parent should be either smaller or greater, depending if it's a min tree or a max tree or a max heap, than either of its children. So you have, the relationship is only between parent and children, right? I know it sounds weird, but bear with me, okay? So this is the parent, this is the leftmost child, this is the rightmost child, and the parent has to be, so the parent has to be greater than either of them, but there is no relationship between the children, okay? Thank God. So parent greater or equal than this, okay? Correct? So if we do this, we get all the, as you can see, I'm only interested in the pop and push operations and their complexities. So the complexities for queues and for stacks are theta of 0, so they won't interfere with my complexity for the overall algorithm. But here I will have to multiply the complexity with logarithm of n at some point, okay? So when I use a queue instead of this C, what happens, okay? Well, clearly I'm gonna put all these elements, the neighbors, inside the queue, right? I'm gonna, first I had the 0 element in the queue, and now instead I took it out here on this line here, and now I put all of its neighbors in the queue. Of course, the first one to be processed is this guy, right? Because it's a queue. So this was the firstly introduced element. So I take it out based on this while loop, right? My queue isn't empty, I take it out. I check its unvisited neighbors, okay? So 2 was already visited, it doesn't comply. But then I put these guys into the queue after 3, right? It goes like this. Let's imagine a queue being like this, okay? So I put its guys, I set them as visited, okay? I'm not gonna get into that. Whatever. And now the whole thing repeats, okay? So I took this out already. Now I have to take 2, and this, as the code says, if it has a neighbor that has not already been visited, I extend it to the end of the queue as promised, and so on and so forth. And as you can see, this is breadth first search. Breadth first means I go and check the directly adjacent nodes to the source node, then the nodes directly adjacent to the ones directly adjacent to the source node, and I do a breadth first search of all the environment. And maintaining this visited data structure, I go through all the vertices only once, okay? So this is easy, right? So this is BFS. I hope you don't consider it to be a BS, okay? Bad joke, I know. Instead, if I use a stack instead of this queue, so let's say I have a stack here. First I'm gonna put 1 here, then I'm gonna put 2. I'm gonna name you 1, and I'm gonna name you 2. Okay, so clearly the one who gets out is 3 first, okay? So I will go from 0 to 3. Then of course instead of 3, the code puts its adjacent elements, but this guy only has 2, and 2 has already been inserted in the queue based on its visited record. So I take 2 out now. Okay, so it goes like this, right? It goes from here to here, from here to here, and now I put all the kids of 2 instead of him. So now I have 1 and 6 in the stack. So then of course the last introduced is 6, who in turn puts 7 and 8 on top of it, right? Clearly I visit 8 first, then I have nothing. I need to pop it. I come back to 6, who has 7, so I visit this as well. Then I pop 7 as well, and then I'm up here, right? So I went as deep as I could. Can you see it, right? Until I couldn't go any deeper. So boom, 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 boom. Then I come back, put it here. Go back, I don't have any kids. This guy doesn't have any kids, right? And then I go back here, and I go here, right? Because now the only one I have here is 1. So I take this guy out, and instead I put the unvisited neighbors of 1, which is 4 and 5. And clearly I visit 5, take it out, doesn't have any children. I go back and try and visit 4, and boom goes the dynamite, right? This is how we do it. Okay, this is of course DFS. Okay? Oh man, I'm so stiff. I mean, my back is stiff. Okay, so sorry man. Okay, so what happens? So the fun part begins when I use priority queues. Okay, so the idea is that whatever. I mean, these are rudimental containers, right? Stacks and queues. They don't really control the order in which I take things out or where I push them in, right? So, on the other hand, in an emergency room, it doesn't, the rule of who gets treated first doesn't adhere to the FIFO or LIFO paradigms. So, now we're cooking, man. Now we can start asking ourselves, who has priority, right? So this is where things get interesting. Like, let's get back to the backtracking, okay? Let's check. Okay, I'm gonna use another backboard if you don't mind. Control A, clean slate. Okay. Just like a convict with a new chance for life. Guys, when you hear convict, don't you think about that Akon song, like smack that all on the floor, smack that, smack that. Do you know, guys, do you know Akon's real name? I mean, I cannot pronounce it. I like the fact that it's a very native African name. That's so good. Okay, so let's see. Let's say we do a little backtracking. So I'm gonna ask a question and I want you to answer, right? Backtracking is what type of search based on this? Like, out of BFS, DFS, and whatever this is. Come on, answer me. Are you still there, guys? Just one small itsy bitsy teeny meeny answer. Anything will do. You can flip for it, man. As a matter of fact, that's a good dynamic to choose between stuff, right? Bă, da, dacă sunteți, answer me this. It's easy, bă. Yes, it's DFS. It's a DFS type of thing, okay? But, okay, you're not wrong as well. Redound 2K9. Te-am născut în 2009, bă? De ce zice 2K9? Man, it's not about the money. It's all about the money. It's all about the dum-dum, dum-dum, and you think it's funny. La memă. Nu știu ce memă, bă. So, well, I don't want to look. It says here that I'm speaking English, man, and you're making me speak Romanian. So, memă. Okay. So, I don't know. Just donate me some cool movies to watch and some good music, and I'm fine. So it's a DFS, okay? So the backtracking works like this. You start progressively creating a candidate solution to your problem, and then you just go deep into the search space, okay? As far as you can, okay? So let's say here, once you've explored this region, you go back, of course, and then you get to this point, okay? So the idea is that all this is bullshit, right? Because it will not lead to any good results, because some constraints from the problem are not met at this point. So that means that neither of these final solutions, sorry, poor choice of words, final candidates do the trick, okay? Yeah, it's cool, but who says which of the variables am I gonna choose? And who says which of the values am I gonna choose first for each variable, right? So I have to prioritize. So that's where things become interesting, right? We go back to the idea that led us here, right? I said that you don't control the order of elements in stacks and in queues, but you do in priority queues, okay? So actually, I don't know if all of you know, but there are pretty fast backtracking algorithms that optimize the backtracking of solutions, okay? Because it really matters how the order in which you search the space, okay? So if you look at the variable set, okay, let's say if you have a problem, you have a set of variables, v of x, okay? So we have vx variables. So for each variable, you have a domain of definition. So you have d for x and y, okay? So this is the domain of definition. So cool, but the order in which you take the variable to tackle drastically modifies the architecture of the tree. You have to agree, right? So let's say I have, okay, let me cut this part out a little bit. Let's say I have a tree. I have two variables. I have a variable 0 with 2 elements in the domain and a variable 1 with 3 elements in the domain, right? So if I start, I have two choices. I can start tackling v0 first and v1 later on, which means I give better priority to v0 rather than v1, or vice versa. So what are the trees that emerge like this? So if I start with v0, v1, okay, first I'll split it into the two possibilities for v0, and for each of the two I will split it into 3 possibilities for v1, right? So these are all the possible outcomes, right? Okay, however, if I chose the other order of variables, I would have first split it into 3, then for each 3 I would have had 2. Do you agree with this? So let's say that these two are the solutions, okay? Or moreover, let's say that, okay, let's say that these are the solutions, right? So now the solutions are stuck together, okay? But okay, let's do it in reverse. Let's say that these are solutions and these are the failures, okay? Because I need to put failures together. Do you agree? Because now in this case, let's say when this value is given to this variable, it all breaks. This is the criterion why the problem breaks, okay? So all this leads to failure, okay? However, these two failures here are on different branches here because of the way the order in which I took the variables, right? So clearly I would like to prefer this approach because I can like eliminate the search for this from the point on than this approach, and this is only done by the way in which I tackle the variables, okay? However, if I was to do it even better, if I was to tamper with the order in which I take not only the variables but the way I take the values, who is to say that I cannot swap between these trees, okay? Or I cannot swap between these trees, which means that I don't take going from left to right with depth first search. I don't waste time looking for this, right? So this one is pushed to the back, right? So the order variables is important because it re-feng shuis the tree on each layer, right? How it looks, how it splits on each layer, okay? And the domain of definition, the order in which we take the values for the variables, it changes it vertically, okay? So, oh, thank you. Okay, good observation. Let me. Better. Oh man. Okay, so what's the idea? If I can manage to push the boundary of search as up as I can by finding the right order to take the variables in, I can reduce the search space, the search process on the vertical. And also, if I can push this as much to the left as I can, even if I have a huge amount of search space to go on, you know, this is the search space, I can try to minimize, to put all my good eggs into a very restricted area based on the permutation of variables I use to tackle the variables and the permutation for each domain in which I give values to the variables, okay? So the trick with backtracking is to try to reduce the search space either vertically or horizontally by finding the best permutation for the variables and for the values for each variable, okay? Which means if I wouldn't have taken this one, but instead I would have taken this tree, the last, okay, then I would have pushed the localization of all the solutions as quick as I could, right? And to the left, okay? So this is why this thing becomes important, okay? I can optimize backtracking for some problems, okay? So if the problem gives you enough clues, so you can, like, at a very early age say, I don't need to search all this space, then you can use backtracking in a very effective manner. And for some problems that are very, I don't know, that give you a lot of hints and you're clever enough to figure it out and you can model them, then you can find all the solutions, okay? You need to understand that this finds all the solution. It's non-negotiable. All the solution, okay? So this is achieved by using priority queues in order to obtain the next variable to tackle and to obtain the next value for the variable to tackle, okay? If you choose, like, of course it becomes a problem in itself, which is the best permutation for variables to choose and which is the best permutation for values for each variable to choose, okay? But if you find that particular permutation, then if you know it, then you can minimize the search space to the minimum, but you will still be doing exhaustive search space, okay? Because we are still in the realm with BFS and DFS, and this guy, which is called the most unpronounceable, no, it's not the most, but one of the most unpronounceable names in computer science. As my colleague once called it, Dikishitra, you know. So, Edgar Dijkstra, okay? So if you take into account the cost it takes each edge in your graph, so the cost, and you prioritize based on the sum of the costs to each of the intermediary states, then, and you put that priority in a priority queue, you have Dijkstra. Okay, so although Dijkstra is more complex and it scares you guys, okay, it's nothing else but the same algorithm as DFS and BFS, but with a different structure, a more cool structure if you will. Okay, so the cooler structure is the priority queue. Okay, and the priority queue is developed by heap, by means of creating a binary or Fibonacci if you're strong enough, but a heap of sorts. Okay, so now, as I stated clearly from the go moment, guys, I care about complexity. Okay, we need to always think about the best complexity our algorithms can have. So now we need to compute the complexity of this algorithm here. Okay, the whole algorithm. We stated that the complexity of the actions we use within the algorithm is O of 1 for add and remove into both stack and queue, and logarithm of n based on the number of edges of vertices we have. In the case of the priority queue. Okay, so now let's check how many steps we performed inside this while. You can see it's a it's like very easy algorithm. It's nothing but a while structure with a for and an if in it, right? So it's like 90% of what people do in the corporate world for their job, right? I'm just saying, just trying to stir up the controversy here. So if you work in like, you don't have to tell me what you do, but if you work in like a firm or something and you do something cool that it's not some aggregation or filtering of data or stuff like that, please tell me, because I want to know, man, the cool projects you do at work. So I need to change these preconceptions I have. Okay. Whew. Okay, so let's see. Question for you guys. Okay, please answer in the. Do you guys know Ray Williams Johnson? Was that the name of that guy with equals 3? He was like in the comment section below. You know? Do you remember that guy from the beginning of the modern internet? So no. Haha, corect. True that. Mamă, de ce nu mi-a plăcut chestia aia când a apărut, man, că era like, man, there's an original already. Why? Yeah, cool. Good. So holla at me, guys, so you know, so I know you're there, because I cannot see how many of you are watching. So let me refresh the page. 43. Man, it's the answer to everything plus 1. Nice. So the question to you guys is, how many times do I pass through the vertices? Okay. I'm waiting for an answer. The vertices are an illusion. What? Correct. So the answer that we only pass through the vertices, through each vertex once, is correct. Let's see why. Okay, so I only push a vertex once, okay? Either here, if it's the case of the, I mean push either here, so I either push the starting point here, or here, okay? But as you can see, the second push action is done within this if. So I will not push it into the container, an element that has already been in the container. Okay, so this guarantees me that I only visit the vertices exactly once. Okay. On the other hand, I have the edges. Okay. So as you can see, this 4 right here gets in all the edges that emerge out of a current node. Okay. But it will not do anything if the edge connects two vertices that have already been visited. Okay, it is clearly established when I pop an element here, it is most definitely a visited one. Do you agree with this? So if this is a visited one, this means it's the current node here. Okay, so I get in this if here, I only get in the nodes that are connected by edges from a visited node to an unvisited node. Okay, so this means that I only go through the vertices exactly once. So if I was to watch the complexity of this loop, it means since I only have, if I have all the elements only once, this while is repeated exactly the number of vertices times. Okay, for each vertex I will go and perform operations in this if from this 4, which only goes at each step at the edges that link visited to unvisited nodes, which means that the overall complexity for BFS and DFS is V plus E, because we can guarantee that we pass through the vertices once based on this policy that I'm not pushing something that has already been visited, and through the edges only once because of the same policy here. Okay, if I have an edge that already linked a visited to another visited node, I don't take it into account, so I only get through all the edges once. Okay, since this is the complexity of the while loop, I need to take care of the complexity of the operations within the while loop. But we have proved that these are O of 1, which lets our complexity remain in the realm of O of V plus E. Cool. How about this one? Okay, so here, of course, we can, in order to pop an element from the heap, I need to perform logarithm of how many elements are there in the heap here. Since I push V, it's gonna be V times, the loop is V times logarithm of V, right? Because the loop is performed V times, and at each time I have this and this actions that give me extra complexity, right? And also these ifs are giving me the plus E complexity for the Dijkstra. Okay, so yeah, this is it. This is the complexity conversation for the search algorithms. Okay, but we didn't discuss one very, very crucial aspect. Okay, this, how much does it cost to check if neighbor is in the set of visit, is in, oh man, I gave away the answer. Domnul diriginte, who that? Bonfire life. You do have a point there, man. I just get too much into it, you know what I'm saying? I'm like Jackson Pollock. Bonfire e domnul Divi. Ah. I don't know, man. I told you. I just need your extra time and your ok. Dar ce-s eu, bă, ăla, cum supărare îl cheamă pe pândău ăla de pe Patreon? Jordan Peterson, frate, lasă-mă în pace. Ok. Okay, so guys, do you get this? So the overall complexity for the basic DFS BFS is O of V plus E, where V is the number of vertices and E is the number of edges, okay? However, I don't even want to be that dude, man. I'm sorry. He's too well dressed. I'm grungy, baby. So, how much does it cost me to check if neighbor is in V? Who's got money on this? Because this is, you can see it's the most frequent call I'm making, right? So at each step, at each while, at each for within the while, I check this if. O of 1, good call, bro. What is the data structure that allows me to search in O of 1? Hash table, okay? So the data structure is hash table, and usually in STL or some other frameworks or libraries, the abstract data type used is unordered set, right? So unordered set implemented on hash table, okay? Do you want to get into the implementation of hash tables with you? Who here doesn't know how a hash table works and wants me to get a little bit into details with that? Let's do this thing then. Okay, let's get into the schematics of it. Okay, so you guys in the first year, you did all this. The last part of the fundamentals of programming course was dedicated to programming methods, right? And first you talked about backtracking, of course, brute force backtracking, then divide and conquer, then dynamic programming, and last but not least, the greedy part, right? So let's go into that as well, okay? Yeah, man, but on the internet it says this is an English lecture, so yeah, I'm sorry. Do you want me to also translate into Romanian? Like I don't know. Yeah, I know. I do have. And the small residual coffee, man. What should I drink coffee at this hour? No. Let me refill my water cup. Okay, when I do this, man, I need to like get some water, but while I do this, just check this video, man. I mean, for sure, you're gonna like it. Blah 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 blah. De ce cânt? Cum o cheamă pe tantea? Lady Gugu. That's not cool. Me? Ra 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 ra. You're in my head, Lady Gaga. That's not cool. Get out of there. the man, the legend. Where is that? The whole interview, okay? This is it, okay? Watch this, man. Okay. I'm gonna go put some water into a cup. Oh. Let me put water first. Bro, I'm not saying I'm gonna give you the video, just check it, okay? Like, this is the video. Okay, I'm gonna... How do I do this? Like, I was just saying that you watch it at home, man. In the privacy of your own environment. Do you want me to do the voice of Bruce Lee, like... When you put water into a cup, it becomes the cup. When you put water into a jar, it becomes the jar. Water can drip or it can crash. Be like water, my friend. Be water. E mai bine așa dacă zic eu? Interlude screen, suntem în Spartacus în 1970 cu intră orchestra acolo, like... Damn. Okay. So the hash table has turned. Let's see what you got. I don't know. I feel musical today, guys. I'm Mary Poppins, y'all. Come on, zic că nu-i cel mai tare, like, character din Marvel Universe, bă. Sincerely now. It's a brim full of ash on a 45. Brim full of ash. So, how you like my nickname, guys? Am I or aren't I? So, I was talking about, can we get back to beeswax, bees knees? So, just I'm ready when you are. Just if at least one of you says go, I'll go. I'll boldly go where no man has gone before. Guys, are you still there? Good. Here we go. Are you breathing? Are you breathing? Ah, nu, că nu trebuie să cântăm Disturb, scuze. Orice numai nu Disturb, bă, că au a one track mind. Trebuie să cântăm Rejoiceful songs. Redemption song. Abba Abba serving the hypocrites along the way. Bă, o să-mi fac și din ăla, cred că. I don't know what that is. Adică, de fapt, trebuia să-i dau ore la un copilaș. Eu, mă, i-am zis că îi dau pe la 6:30, dar nu cred că apuc acum. Holy shit, bă, dar câte mesaje am azi. Crazy. What that? Oh. Royalty in the house. O să ascult mai încolo, mersi, boss. Rabdă inimă și tu. Rabdă inimă și tu. Okay, so I was saying about programming methods, right? So first you have the slowest, the most thorough one of those, the one we started, backtracking. Okay, you take everything, you exclude you exclude the improbable, and what we have to have it in the end, it must be the truth, right? Man, I don't know how to say it like Sherlock Holmes, you know, but you got my drift, right? So that's backtracking for you, okay? So the other technique is divide and conquer, okay? If you can split the problem such that you can solve independent parts of the problem, okay? Then you can perform a divide and conquer technique, okay? And the divide and conquer technique usually gives a better complexity in the sense that it takes one of the ends in your complexity and turns it into a logarithm. How does it do that? Well, let's take the most classic search algorithm possible. When you search into an array of elements, right? The best algorithm to do so, if your data is sorted, okay, so I'm going to illustrate it by illustrating the value of the elements as growing from left to right. So if you have the algorithm on a sorted array, you clearly use binary search, okay? So binary search is, of course, a very clear example of divide and conquer technique, okay? Because you say, okay, if the elements are sorted, țară faină, burn fire live, dar zi-mi cine ești măcar, bă. So, evil cookie, what do you mean for the students from third year? Which third year? Romanian, engleză? Petru de la 217. Have a good night and good luck, son. So, evil cookie. What do you mean for the students from third year? Just tell me what your specialization is, okay? Now let's see. Okay, so let's go on, okay? Considering we have an ordered linear structure, like an array of ordered elements, having the left position and the right position, and computing very easily the middle as the left plus right over 2, okay? If I check the value of the element I'm looking for against this value here, I can have 3 cases. If it is the value I'm looking for, I'm done. Everything is okay. If it's smaller, I don't have to look here. And then I move like this. And if it's greater, I don't have to look there and I move to the other side, okay? So at each step, my search space splits to 2, right? And I can go on and split half and half this search space up until there's no space left at all. At the least, I'm remaining with one element, and the worst case scenario is that I've searched the whole space and not even this particular element is what I'm looking for. So clearly, first I look in an n length environment, then n over 2 and n over 2 to the power 2, because I keep dividing by 2, right? Up until I reach one element, which is n over 2 to the power how many steps I took, right? Just look at it. So first I take one step to verify this guy, then I take one step to verify this guy, and then one step at each level. So the k number of levels up until I reach only one element gives me the number of steps, the comparisons I take to find to locate the element I'm looking for. If I take k mathematically out of the equation, it says that 2 to the power k equals n, and of course k is the logarithm, right? Easy, right? Easy AF. Okay, so this means that usually if I split the universe I'm looking for into halves and then that half into halves and so on, I can reduce the time complexity for the search if I have some particularities, right? Sorry, I'll move the image. It's cool. Okay. Okay, so yes, the thing is, why stop at splitting things only in half? Okay, why? I could split them into 3 parts, right? I have logarithm in basis 3 then. Okay, or logarithm, let's generalize all this approach and say I split it into k. Logarithm in base k over n. Okay, so this is the beginning of the philosophy for hash tables. Okay, the father, are you still with us? Cool. So the idea is that, let's say, if you have elements from 0 with values from 0 to 500, okay? 0, and you have a file with a lot of numbers, but you know that all the numbers in that file have values between 0 and 500, okay? So usually, in order to store this information, you will not use an array of how many numbers you have, but instead you will use a frequency array, right? So since 500 is a small amount of numbers, right? I'm just gonna use an array holding with 501 elements, holding at each position the occurrences of that particular number, right? A frequency vector, okay? So first, I only occupy 501 positions of numbers without even, let's say I have like 10 to the power 46 elements there, okay? Not quite, it's too much, okay? 10 to the power 8 elements there, okay? If I have 10 to the power 8 elements, the numbers here can be, if all the elements, you have 10 to the power 8, the extreme case is that you only have one element that occurs 10 to the power 8 times, okay? Which means this number has to be able to be stored within a long, which is 2 to the power 64. Okay, so if you have this, you will use a frequency vector, right? Okay, this is easy, right? It simplifies a lot of stuff for you, okay? So the guys from the first year, quick problem, okay? I have a file containing a huge amount of numbers from 0 to 500. So, and I ask you queries in the form AB, like this, with A smaller than B, and you have to tell me, with the best priority, how many elements are in the interval AB. Can you give me a solution? Guys? Exactly, anybody? Remote worker, how about you? I'm gonna wait 1 more minute at most, and then I'm gonna tell you the answer. I bet you guys know the answer, right? So if I'm telling you how many numbers are there between 15 and 201, 201, yeah. And then I'd give another query from 7 to 0, or to 10, sorry. From 11 to 500. You know, I need to optimize this. Okay, that is the problem. Yes, but I need to perform something first. It's cool, but what I need to do is first I need to partially sum all the elements from here. So I need to go from here to here, and I need to say that let's call it the frequency f of x, x being the position here, or f of I, let's call it I so it's not confusing. It's in fact f of I plus f of I minus 1, right? Right, so here I'll have the sum of the, this is only the sum of the first element, the sum of the first 2 elements, the sum of the first 3 elements, and so on. So in fact, in order to find out how many elements are from an interval, you compute f of this one minus f of this one, but not particularly this one, but the element before it. So this one minus 1. Cool. So what you didn't realize is that you are in fact computing integrals, like literal integrals, right? You know, do you remember the integrals? Like you have a function, you have the graph of the function, and then this area here from A to B, this colored area here, is in fact the definite integral from A to B of f of x dx. Correct? So if you remember from high school, you will use primitives to define it, like f great f of b minus great f of a, with when f is the function that is derived to f, right? Right, so that's how it works, man. Like, guys, if you were in I don't know, there some third year students in the audience? This also correlates with statistics, man. Like, think about it. You have the PDF and the CDF, right? You learned about this in school, right? So the CDF is nothing but an integration of the PDF, right? Because it's the cumulative distributive function. It always goes to 1, right? So, yeah. So integrals are nothing but sums taken to the limit, okay? But this was just a small divagation from the actual subject, okay? Because now we're gonna complicate the issues a little bit, okay? I know you enjoyed this one. It's cool. I know you knew how to solve this problem. Cine ești Tudor? Tudor. Yeah, man, you should watch a Romanian movie called Iancu Gianu, man. If you haven't. It's badass, if you ask me. So, math is beautiful, man. And that is why, instead of having integer numbers from 0 to 500, let's say I have real numbers from the interval 0 500. What changes then? Okay, I have floats now. Can I use an array to store floats? Like, can I use indices to store floats? Right? I cannot. The indices themselves are integer numbers. 0, 1, 2, n minus 1. So, what do we change here? Converts to string. Holy shit. But you need to use hashes for that, and now we're explaining hashes, my friend. You cannot do that. You know what I'm saying? So, convert to string. Good one. Good one. Okay. It has been established that you can do life hacks, man. Convert to string. I like that one. Whoa. Too much water. It's cool. It's cool. Sipping whiskey off the bottom, not thinking about tomorrow. Singing Sweet Home Alabama all summer long. Man, those were the summers, man. So, I need something more, I don't know, basic than your solutions, guys. Let's say, I cannot put all the... How many... Okay. Question. Okay. How many numbers, real numbers, are there between 0 and 500? Correct. An infinity. So, correct. An infinity of infinities. Okay. So, what we need to do is to figure out how to store them somewhere, somehow. Okay? Man, I'm bad at this. I'm bad. So, I'm gonna use the same vector, okay, with indices from 0 to 500. But now each position will refer to a subinterval of this space, okay? I will split this into equal sized subintervals from 0 to 10, from 10 to whatever. Okay, so let's say I have 50, and I will put all the elements that are from 0 to 10 here, all the elements that are from 10 to 20 here, 20 to 30, 30 to 40, blah 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 blah. Correct? Do you agree? So the idea is that now I cannot store only one element on one position in this array, right? So there will be crashes. How do you call clashes? Another term for clashes. right? There will be collisions, meaning that if I have more than one element in one of these sub-intervals, they will have to occupy the same space, and you know that physics prevents that from happening. So we need to find a way to avoid this, okay? Can I erase the table, the blackboard, guys? Boom. Thank you. So the idea is I'm using a vector of n elements, okay? And each element, in fact, element in the vector represents what they call a bucket, okay? So this is one bucket that can hold multiple elements. Then this bucket holds all the elements from 0 to 10. This bucket holds other elements from 10 to 20, 20 to 30, so on and so forth, okay? So actually, the quickest way to store them is in linked lists, okay? We talked about them before, right? We talked about them in the first year. The guys from the first year, you're just talking about them, okay? But those are easy, man, come on. So let's say I have one object, I put it here. I put another object here. If not, they're null, okay? If you don't have any objects so far, you just set them to null. You just add some objects, okay? So the addition at the beginning or at the end of a list is theta of 1. It doesn't require extra calculation. So every time if I find another object that falls into the same bucket, I just add it to the designated linked list. Okay? Cool. So now, if I still hold the number of elements in each of the lists, like as a number here, I know how many of them they are. So the structure of the list also holds the number of elements. I can solve the same problem as before, but now with floats, right? Because now I do the same thing. For each, I will say f of b, get the number from that list dot nr minus f of a minus 1 dot nr. Okay, so it's the same solution, but now with floats, right? So I go once through all the elements in the file. These are floats now. Now I need to find a very effective way to find out in which bucket I put it, right? So I just take the, how do you call it, integer part, right, of the element. Take the integer part of the element, and that integer part I just put it modulo 10, let's say. Right? Do you agree with this? Guys, are you okay? Just at least one confirm. The father, is you following? Okay, remote worker. State your claim. La 111. Let me think. Că l-am și pe 500 ăla sau ce? Yeah, whatever. Okay. Remote worker, you might be right, let's see. La 100, I have, because I have that 500 one, right? Okay. Yeah, but let's exclude that 500. I have from 0 to 499. Is it better for you? this is a cool discussion. We're entering a cool discussion here from the artificial intelligence point of view. Do you sacrifice what works well for the norm in order to go and optimize it for the outliers? You know, that's an idea you need to remember as we progress. Okay, but we're just at the beginning. Okay, so you have to agree that this works, right? It still gives me the defined integral, but now with the with floating point numbers. Okay, but now without even knowing, we kind of created a hash table somehow. Okay, because now the object x is a float, right? So I needed to find a way to figure out where to put it. Okay, so since we consider that each number from 0 to 499 has the same chance of occurring, then it means that we can create a uniform distribution by splitting the whole space into equally sized spaces. Okay, so it means that for each of these subspaces, the average number of elements that are located in the file is uniformly distributed. Okay, so now I have one x, and the problem is that I need to find the bucket in which to put it. Okay, so in order to do that, I need a function that takes x, which is some sort of an element, it doesn't matter what it is, and gives me a number, an integer number, which is the bucket, the code of the bucket in which to put it. Okay, this function is called a hashing function. Okay, so it's a function that takes an element from a domain, and in a very straightforward mathematical manner, without additional complexity, I would like this hashing function to be in the realm of 1. Okay, I don't like it to be very computationally expensive, because it's gonna be used all the time. Okay, in this data structure. So the hashing function just gets an element from whatever domain, now it's float, so, and gives me the designated bucket number for that element. Okay, once it does so, it takes me theta of 1 to add it to the collection, to the hash table. Okay, so in fact this is a table, that's why this is called a hash table. Okay, so this is a hash table because if you look at it, it's sort of like a table. You find the bucket and then you search through. It's like columns and lines, or columns. Okay, so it's a table. So what's the idea here? Why? Because some guy from the audience said that I can search in O of 1 in a collection like this. Okay, so we already established that if I had an organized or a sorted environment, the most I can do for searching is log 2 of n or log k of n by doing binary searching. Okay, but if it's not ordered what bothers me, and the elements can be unordered, I can find a way to improve the complexity of this operation. Okay, so by doing this, okay, I don't care. Okay, I don't care of the order of elements. Here it just so happens that they're also ordered. Okay, but by the buckets are ordered. Okay, but the elements within the list, they're not, because they arrive in whichever manner they arrive. Okay, so these lists don't contain ordered elements. Okay, but the idea is for any container to optimize three actions, three functionalities that are general to any container: add, remove, and search. Okay, so let's see what the complexity is for a hash table for each one of those. Okay, so for addition, I take an element x. I don't know, it's just an element from the domain. Okay, in theta of 1 or in O of 1, I compute the bucket to store it. Okay, so I don't waste time there. And then in another theta of 1, I add the element to a linked list. Okay, so the addition costs me O of 1. Okay, how about removing? Okay, so if I was to remove something, I would do the same thing. I say, okay, remove this element from the collection. Compute in O of 1 the bucket, and now I will go, let's call this the number of elements, the average number of elements inside this linked list. Let's call it alpha. Okay, how much is alpha if the chance of any element to go in any bucket is uniform? Who can tell? So each object has the same chance of arriving in each of the buckets. If I have n objects and n buckets, what do you mean 1? 1 is the loneliest number, man. N over n. Correct. So the uniform split of all the n, capital N elements into small n buckets gives me on average alpha. It's cool, it's cool. Good answer. Gives me on average alpha elements in each bucket. Okay? But this alpha is dynamic in time. You agree? So actually I get O of alpha complexity for removing an element, because I need to search in a linear fashion in this particular arrays, right? Linked lists, okay? And this has to be done linearly, but the length of the list has been proven if the hashing function gives a uniform split of the elements in buckets, that on average you have at most alpha elements in a bucket, right? That goes without saying. I mean, it's kind of straightforward from a mathematical point of view, okay? And also from a statistics point of view. Alright, so how about search? Search is just like removal, but you just don't remove it, right? So you still have O of alpha. And now's the tricky bit, man. We need to maintain this alpha to be between 1 and, let's say, 1.14 or something. Let's say, how? Do you know the literature? Who knows the literature? How much should the loading factor be usually in hash tables? 1.4, I guess. You cannot go. Correct. Okay, so let's see. What does this mean? Okay, if alpha is the length, the average length of the lists on a bucket, it means that you have between 1 or 2 elements in each bucket, okay? Which turns this alpha into almost O of 1, okay? So in order to maintain O of 1 complexity for both search and removal, we need to maintain this alpha within these limits. And now we will see what can influence this alpha, okay? So what happens if I keep the n constant, the number of buckets constant, and I do a lot of addition operations? This guy blows through the roof, right? and this guy remains the same, which means that also alpha blows through the roof. That means as I put stuff in the container, and this, exactly, that's the way to go. So when we approach this limit here, we need to increase this such that this one decreases as much as we like, right? So we need to perform some rehashing, okay? What does rehashing mean? You can see here, this is hard-coded here, right? Because here we have small n. Let's go back. So usually this function, which was the integer part of the element, is usually divided by the number of buckets, which is straightforward, right? From a mathematical perspective, if you get a modulo n, it will give a code from 0 to n minus 1, which gives you the code of the designated bucket, okay? So the thing is, we need to find a bigger n prime, bigger than n, so that having this constant, we decrease the alpha, okay? So what we do and how we do this is very simple, okay? We just take another array which is longer. It's not n, it's n prime. And this one is like new right now, okay? It doesn't have anything in it. And now we compute the same. Look, this doesn't change. The function, we take all the elements from here, we iterate through all the elements on all the list, and then we recompute what? Instead of doing modulo n, we do modulo n prime, and clearly this will spread on a wider surface of buckets, right? This means that the overall length of elements now rehashed all throughout the buckets will be alpha, which is now smaller and contained within this realm. So from time to time, after each addition, we check if this alpha is cool. If the alpha gets into the danger zone, we perform a rehashing operation, and the rehashing operation has to go through all the elements. So rehash, I'm gonna say here, rehashing clearly takes O of n steps. And you're gonna be asking me, okay, but then why bother, right? Why bother with the rehashing if it takes O of n? O of big capital N, because it's the number of elements inside the table, okay? So in order to I don't know, have you guys checked in your Visual Studio the status of your memory? Like visually, there is a visual depiction of the memory, and you should check it out, man. Like when you implement for your data structures and algorithm class, when you implement your operations on the big tests, okay? Because it looks something like this, like, I don't know, stuff like that, then it goes like this, then it goes like that, and it goes like this, and so on and so forth, okay? In spikes, okay? But let's see what happens with the complexity as we do a lot of add operations, okay? So we said that the add operations on a hash table only takes up O of 1. So if I do a lot of O of 1 operations up until the cumulative effect that is that I introduce n elements, O of 1 at a time. So at a time I just introduce a new element, but here in this point introducing 1 and 1 and 1 ce înseamnă MW, bă? Modern Warfare, man, that's the game that got me out of playing games, man. That bullshit game. It's like Call of Duty 2 or nothing. Annoying story, man. Like first mission in Baghdad or somewhere, and you just like, I got killed off in a nuclear blast, and I was like, screw you, movie. I mean game. Whatever. Okay, don't get me distracted. So if I perform a lot of additions, yeah, I do a lot of add operations. At this point in time here, I'm having a very huge n over this n, and alpha, my alpha is 1.40, let's say, okay, close to this. So I need to waste n operations to move the elements, okay? So in a spike, I do n O of capital N operation, okay? Then I progress into doing other O of 1 operations up until I get another huge n that gives alpha again, puts it close to 1.4, which means I cannot. Why do I care about this? If alpha is greater than 1.4, I cannot guarantee that O of alpha is in fact comparable to O of 1, because I may have 3 elements or 4 elements inside the small linked list. So when this shit happens, on average, I cannot demonstrate mathematically that this tends to be O of 1, so I need to remedy that. So I perform more n operations, a bigger n, right? It's a bigger n, okay? And so on and so forth, okay? But hear me out, okay? This operation is just like when you build sand castles and you take a truck and you go through the sand castle, okay? If I take one by one the n steps it does in spikes here, and I put this one over here and this one over here, it's identical to me having made 2 steps every time, which is in fact an amortization of this very demanding action over time. If I was to compute how many actions over time I've done so far from here to here, it will give me 2, okay? It's the same here, okay? If I was to compare how many operations I did, I take the sum of all the number of operations over the amount of time spent, it will take on average 2 operations over time, which is still O of 1. That's why we say that if we perform this rehashing from time to time, but only when this alpha begins to become bad, I can guarantee. Bă, nu 1.6, că eu ziceam de 1.4. Deci serios, eu v-am zis de 1.4 și vă făcut să vă gândiți la counter, bă. Copii și haine rele. Okay. So guys, are you still paying attention? Because you're like distracted by games, man. Was my favorite game? So depends on the genre. For football is FIFA 2007, I guess. For basketball is NBA 2003. Damn. And for driving, of course, Underground 2. For shooters, Call of Duty, the one with the missions in World War II, and Call of Juarez. Yeah, I like FIFA 08 as well. And one of the best gaming experience I've ever had as a kid, Dave Mira Freestyle BMX, man. I highly recommend you the soundtrack. You know, like the soundtrack is the best soundtrack. It beats Underground 2, it beats Tony Hawk Pro Skater. I mean, come on. But okay, let's get back. Do you understand this? The fact that yeah. Thanks. See, man, these guys get me distracted, man. I don't know. No school like the old school, though. So the thing is that you do some computation, but very rarely, and it's amortized with time. Okay, so in the long run, you win more than you lose in spikes. Okay, so at the end of the day, the complexity of adding, removing, and searching operation on a hash table is O of 1, which gets us back to this particular line of code that's checked if a neighbor was in V. Okay, so that means searching. Okay, so if I have V implemented as a set on a hash table, I don't get any additional complexity to this search. If I was a noob and put it into an array, of course this V will have multiplied with the search it takes to check whether the element was visited or not. But now, if I'm cool, this V will be implemented on a hash table. This is why you need to know your data structures, guys. I mean, come on. This is look at this. It's a very straightforward algorithm, right? So, but in the back, it uses almost all of the data structures you need to learn, right? In order, because I said it at the beginning, we need to optimize it, right? So, the thing is, you need to optimize the actions of all these functionalities. Push into the visited, push into the container. They all have to be implemented at their best time complexity possible, so that you ensure that the algorithm performs as fast as it can. For that, it takes nuance, okay? It takes knowledge of data structures and algorithm, and that is why when you go to an interview, they ask you that, okay? Despite the fact that you now create memes that it's a hardcore interview and then you go and become a front-end developer. Okay, I get that. But still, it doesn't mean that they shouldn't ask you those hard questions. Those aren't hard questions, okay? Those are they are front-end development, okay? So, I don't know, that's the beautiful part of computer science, man. That's the art of algorithms. Like, not only we will see in all this story about artificial intelligence. You don't have to just find the solution, okay? The greatest chess players don't just find the solution. You need to find the solution with the least amount of effort possible, okay? Because this is like what nature does, right? Because everything takes the form that occupies the least energy, right? That consumes the least energy in order to preserve life. So your code as well should strive to do its task with the least amount of effort and energy possible. Okay? If nature does this, man, like you have a protein and it folds in like a nanosecond into the tertiary form of it, like SNAP, such that it maintains life by not consuming more than it produces. You should find the same approach when you code. Don't just settle for like writing code that does the trick, okay? That is not what computer science is about, and that is not what the artistic part of computer science is about. The artistic part, and what any computer scientist, if you will, should need to start from, is to try to optimize everything, okay? So, as I said before, in my opinion, computer science is the art of solving problems, like real life problems, in the most efficient way possible, okay? So, yeah, of course, yeah, the father, I get what you're saying, that aurea mediocritas, as the Latin said, right? We will see in what follows that you need to find balance, okay? So the best approach is find some middle ground, okay? Because if not, all the context of the great problems lead you to either win some to some extent, but on the other hand, you lose some, okay? So what you need to find is a saddle point in which you lose the least from any perspective, okay? So yes, this optimization, an overall optimization, requires finding a balance and an equilibrium of things, you know? I get that, but it's still optimization. So, where was I? So, guys, I will go up until the 8 hours, ok? Dorel, bă! Ce tare ești, bă! Bine, Ionuțaș, m-ai făcut de faza... Ești tare pe net, bă! Floyd Marshall... Yeah! Maybe, but... I don't know, let me see where I'm going with this, okay? Because I had a vision, an overall vision, okay? So I see up everything with Ned. I don't know how to read your name, man. Okay, so let's get back to this. Learn your data structures. That was the topic, okay? Learn your data structures, learn your algorithms, okay? Because the algorithms are based, as we well have seen, on the data structures, okay? The algorithm is just a succession of actions, but the complexity of the algorithm, the actual complexity, can only be given when you implement it using actual data structures, okay? So I cannot talk about the actual complexity of this algorithm up until I know which is your implementation of this V container, of the C container, and so on and so forth, okay? Once you implement it, you give the actual time complexity to that algorithm. So what we've done so far is that we covered exhaustive searches, okay? So you can see that starting from brute force and backtracking, we go and we scan the whole perimeter, right? And then we talked about DFS and BFS, and we realized that in fact brute force and backtracking are DFS algorithms that again exhaustively search the search space, okay? However, from the point of view of the quality of the solution, so yeah, okay, I'm gonna ask you, what do you think if you model a problem with this type of search space, right? Like a tree or a graph, okay? What will be the measure of how good a solution is from your point of view? Like, think about this. If you have two players in chess, let's say, maybe it's not the perfect example, but one of the players can reach the victory on average in, I don't know, 7 moves starting from the current situation, and the other one gets there in 13 moves, right? So it's a time issue. You're a better chess player if you reach the state in which you win with the least amount of intermediary states. Prove me wrong. Do you agree with this? Say yes if you agree. I'm just saying. Okay, so maybe a measure of the quality of a solution is the length of the path that leads from the initial state to that particular state you found, right? So, yes. Yeah. So that means that if I go with the depth first algorithm, usually I get a solution, right? But I never locate the optimal solutions first, right? If it's the length of the edges, the length of the road, the, how do you call it in English? Not chain, it's path. Okay, the length of the path that counts. Breadth first search guarantees, do you agree? It guarantees that it will lead to the best solutions first, because it goes like to the nearby elements, then to the nearby elements, and to the nearby elements, so on and so forth, right? So okay. No, I'm gonna change the blackboard from the top, okay? So the idea is, this is just for illustrative purposes, okay? I'm gonna change the color. Cool. So blue is this, man. I'm colorblind, man. You're killing me here. Okay. So when you have a in-depth, okay, let's say this is a solution here, okay, and you have another solution here, and if you use depth first search, you will get to this solution before you get to the other one, okay? Whilst when you go breadth first, you will get to that solution first because it's closer to your initial, okay? So yes, breadth first ensures okay, so the idea is that breadth first search guarantees you find the best solution first. If the measure for the quality of the solution is the number of intermediary steps you take until you reach it, okay? But however, it has a drawback, right? Because it takes very, very, very long, okay? So this is what I wanted to tell you about searching with exhaustive algorithms, right? So in all these searches, you just scan the perimeter, okay? So if you scan the perimeter, you will waste time, because for real problems, even this small perimeter is close to infinity. It's very, very huge. So what do we do that? What do we do then? When still, if I reduce the backtracking to its minimal form, because I know the best permutation for values and variables that occurs, it's still close to infinity and still NP complete. What do I do then? I need to stop being so strict about finding the optimums. Okay? And now we're getting into the realm of real AI. Okay? Because this, all the bots playing games, this was in the 60s, you know. The guys from ARPANET, you know ARPANET, the guys who built the internet for the army and shit. So those guys were playing with what? Like they played with two types of games, right? They had a software that was playing chess, and they had some software that was imitating a psychologist or something, based on some expert system done for the psychology domain. Okay, and they were playing with this kind of artificial intelligence. So up until the 80s, let's say, people focused on solving games with computers, like creating entities like bots to play games against humans, or to learn how to play games better. And then there was all this fashion with devising expert systems. So if you had a huge knowledge base about the system, they created some if-then rules in order to help us, or to replace a human for different tasks. Okay, so for medicine diagnostics, okay, of course nobody can replace House, that's for sure, right? But they did create at the beginning, and it was employed in some hospitals for the more simple diagnostics, an expert system that actually learned from a various amount of data from patients and stuff like that. If the patient had some sort of systems, it will like use some if-then statements to guide it to be classified into a different diagnostic. So this is what the people did first, okay? But that is not what passes for artificial intelligence nowadays, okay? Because things have gone way beyond that level, right? So now I'm just gonna take a small bathroom break, sorry, okay? And then we'll follow up with some non-exhaustive search techniques, okay? You're gonna love them, I promise. Stay tuned, dudes. Just a small break, okay? Please don't leave, okay? I'll be back in 5 minutes, okay?